Renuka Devi is an assistant professor at the Department of Statistics, Presidency College, Chennai. Mrs. R. Renuka Devi has done her MPhil from Madras Christian College. She has 23 years of teaching experience and has published one research paper. She has also presented, participated, and organized conferences and workshops on statistics-related subjects.
Welcome to UGC lecture series on mathematical sciences. Under the topic analysis of variance, in today's lecture, the topic under discussion are analysis of variance, introduction, definition and assumptions, one-way classification and two-way classification. So, we have introduction to analysis of variance. The term analysis of variance was introduced by Professor R.A. Fisher way back in 1920 to deal with the problem in the analysis of agronomical data. The analysis of variance is a very powerful statistical tool for test of significance. Test of significance for the difference between the sample means. In the case of two samples, the appropriate test is t statistic, but we have situations where we can have more than 3 or 3 samples under consideration at the same time. So, in that situation we need an alternative procedure, and the solution is provided by the technique analysis of variance. Analysis of variance, we test the hypothesis that the samples are drawn from the same population or with the same mean. Basically, analysis of variance is a tool to test the homogeneity of several means, and it is a known fact that in any numerical data the variation is present, and the total variation in the numerical data may be due to number of causes. So, here we have a classification of causes, assignable causes and chance causes. The variation due to assignable causes can be detected and measured. Chance causes is beyond the human control and it cannot be traced. The actual definition here we have for analysis of variance, it is the separation of variance ascribable to one group of causes from the variance due to another group. By this technique, the total variation in the sample data is expressed as the sum of its non-negative components, where each of these components is a measure of variation due to some specific independent source, and it consists in the estimation of the amount of variation due to each of the independent factors separately, and then comparing these estimates due to assignable factors with the estimates due to the chance factors. So, it involves two phases. In the first phase, we estimate the amount of variation due to variable factors, and the second stage, the comparison between the variable factors, that is comparison of these estimates by the different factors is carried out. And we have the assumptions to carry out the analysis of variance. For the validity of the F test under analysis of variance, we have 3 important assumptions. The observations are independent, parent population from which the observations are taken is assumed to be normal, and various treatments are and environmental effects are additive in nature. And the sequence we are going to study analysis of variance is given. So, first we are going to discuss about one-way classification, and the second topic is two-way classification. Now, one-way classification, here the total observations, that is n observations, we do not denote it by yij, and here I ranges from 1 to k, j ranges from 1 to ni, say for a random variable y, are grouped into k classes, each of the k classes of size n1, n2 and so on nk respectively, so that the total number of observations n is equal to sum of all these n values. And one-way classified data, so we have an illustration. So, we have k classes, and for each of the k classes we have sample observations. Sample observations total, and for all these classes we have separate mean. So, classes we have 1, 2, up to k, and sample observation first class, the sample observations are denoted by y11, y12 and so on, yn1, the total is t1 dot and the mean is y1 dot bar. Second class we have y21, y22, y2n2 with total t2 dot and mean y2 dot bar, and for the ith class we have I1, yi1, yi2, yini with the total ti dot and yi dot bar, and for finally for the kth class yk1, yk2 and yknk, and for the kth class the total is tk dot and the mean is denoted by yk dot bar. The objective of one-way classification is to examine if there is significant difference between the class means in view of the inherent variability within the separate classes. So, the total variation in the observations yij can be split into following two components. Number 1, the variation between the classes or the variation due to different bases of classification commonly known as treatments, and the second one is the variation within the classes. Now, here we have an illustration for one-way classification. Let us consider the effect of k different rations or treatments on the yield in milk of say n cows, and let us divide these n cows into k classes of sizes n1, n2, nk respectively, and as we have defined earlier, this capital N is equal to summation of ni, small ni, I ranges from 1 to k. So, here the sources of variation, that is the variation of milk, yield in milk is due to the different components. Here we have the different types of components. Number 1, the effect of the random treatment Ti, since here we have k different rations, I ranges from 1 to k, and the second factor is error. Mathematical model for the given illustration is defined as yij is equal to mu plus alpha I plus epsilon ij, I ranges from 1 to k and j ranges from 1 to ni. Yij is the yield from the jth cow fed on the ith treatment, and here mu is the general mean effect, and alpha is the effect due to the ith ration or treatment, epsilon ij is the error due to chance, and the assumptions for this model are all the observations are independent and follows normal distribution with mean mu I and variance sigma I squared, and different effects are additive in nature. Also, epsilon ij's are IID normal, that is identically independently distributed as normal with mean 0 and variance sigma E squared. And here we have the statistical analysis. To perform the analysis, first we frame the null hypothesis. Here we have the null hypothesis that mu 1 is equal to mu 2 and so on, mu k is equal to mu, and or alpha 1 is equal to alpha 2 and so on, alpha n is equal to alpha. Mean to say that the effects due to the different treatments or rations are homogeneous, and against the alternative hypothesis that at least two of the means mu 1, mu 2 and so on, mu k are different. And now we will find the least square estimates for the mean mu and the parameter alpha I, and these two are estimated by the principle of method of least squares by minimizing the error sum of squares given by E, which is nothing but double summation of epsilon ij the whole square, that is obtained from the model defined earlier. So, here you have yij is equal to mu plus alpha I plus epsilon ij. Keeping the epsilon ij on the right hand side, taking other two terms to the left side, squaring and taking summation, we get E to be double summation epsilon ij the whole square, which is double summation of yij minus mu minus alpha I the whole square. The total variation in the data is partitioned into different sum of squares. So, here we have total sum of squares as sum of squares due to treatments and sum of squares due to error, and which is represented by ST squared for treatment and SE squared for error square. Different sum of squares, we have the degrees of freedom. The total sum of squares is computed from the n quantities of the form yij minus y double dot bar, and it will have n minus 1 degrees of freedom. Similarly, the sum of squares due to treatments and errors will have k minus 1 and n minus k degrees of freedom respectively. And mean sum of squares, this we have already discussed in the previous lecture. The sum of squares divided by its respective degrees of freedom gives actually the corresponding mean sum of squares or variance. So, here mean sum of squares due to treatments is obtained by dividing the sum of squares due to treatments by its respective degrees of freedom, that is ST squared by k minus 1, and mean sum of squares is denoted by small letters. So, here you have small st squared. In same way, we obtain the mean sum of squares due to error by dividing the sum of squares due to error by its respective degrees of freedom. And to test the null hypothesis, we have the test statistic defined by f is equal to st squared by se squared, and it said to follow f distribution with k minus 1 and n minus k degrees of freedom, and this is supposed to be the observed value or calculated value. We compare this calculated value with the table value at a particular level of significance, say 5% or 1%, and if the observed value of f is greater than the table value at a specified level of significance, then H naught is rejected, otherwise we fail to reject H naught, that is we accept H naught. And the entire analysis can be put in a form of table called ANOVA table. So, we have ANOVA table for one way classification. So, it consists of 5 columns. First column, sources of variation, sum of squares, degrees of freedom, mean sum of squares, and finally we have variance ratio. So, under sources of variation we have treatments or ration, error. So, combining these two we will get total. Sum of squares due to treatments, this is denoted by capital ST squared and this is capital SE squared. So, here it is k minus 1 and n minus k and n minus 1. Total sum of squares is denoted by capital ST square, and mean sum of squares, as I mentioned, it is obtained by dividing the sum of squares due to treatments by its respective degrees of freedom, and here we have mean sum of squares due to error, and finally f ratio, this is defined by f is equal to st squared by se squared. It follows f distribution with k minus 1 comma n minus k degrees of freedom. Now, we will move on to the next study, that is two-way classification, and here the n observations are classified according to two categories, say 2 factors. So, here the categories being A1, A2, AK due to A, and another category may be denoted by B, and the categories under B are B1, B2 up to BH. And AI comma BJ is nothing but the cell. This scheme of classification is called two-way classification. So, here I ranges from 1 to K and J ranges from 1 to H. And in two-way classification, the values of the response variable are affected by 2 factors. So, here also we have an illustration. So, same illustration with a small modification. We have here n cows divided into H different groups according to their breed and stock, and each group containing k cows, and then let us consider the effect of H treatments on the yield of milk. So, in one way classification, the yield of milk is assumed to be affected by only the effect of different treatments or rations, but here the other factor has come into study, that is the breed and stock of different cows. So, here the yield of milk may be affected by differences in treatments as well as differences in variety. So, Yij be the yield of milk from the j-th cow or cow of the j-th breed fed on the ith treatment. I ranges from 1 to k and j ranges from 1 to h. And the two-way classified data. So, here we have treatments as one factor and varieties of cows as another factor. So, here we have H varieties and under treatments we have K types of treatments. So, since it is a two factor analysis or the Yij affected by two factors, we have both row total, row mean and column total, column mean. So, here row total and row mean, and finally we have column total and column mean. So, the observations are Y11, Y12, Y1j, Y1h, and here it is T1 dot Y1 dot bar, and for say ith treatment it is Yi1, Yi2, Yij and Yih, and the total is Ti dot and mean for the ith row is Yi dot bar, and finally we have kth treatment Yk1, Yk2, Ykj and Ykh, and for the kth row the total is Yk dot and row kth row mean is Yk dot bar, and similarly we have column total is T dot 1, T dot 2 and so on, T dot j, T dot h, and both way if we add we will be getting the total number of observations. So, both column total and row total gives the same value, which is capital N, and column mean we have here Y dot 1 bar, Y2 dot bar and so on, Y dot j bar and Y dot h bar. And mathematical model for a two-way classification is given as Yij is equal to mu plus alpha I plus beta j plus epsilon ij, where Yij is the yield from the jth cow fed on the ith treatment, mu is the general mean effect, alpha I is the effect due to the ith ration, beta j is the effect due to the jth variety of cow, and epsilon ij is the error factor due to chance, and Yij are independently normally distributed with mean mu ij and variance sigma squared, and epsilon ij's are IID normal with mean 0 and variance sigma e squared. And the null hypothesis to perform the two-way classification is that the treatments as well as the varieties are homogeneous, that is there is no significant difference between the effects due to the treatments as well as varieties. In notations we have H naught T, that is null hypothesis for treatments, as alpha 1 is equal to alpha 2 is equal to and so on, alpha k is 0, and for varieties it is H naught V, beta 1 is equal to beta 2 is equal to beta k is equal to 0. And alternative hypothesis denoted by H1 T and H1 V, that is at least one of the alpha i's is not 0 and at least one of the beta j's is not 0. And here we have the least square estimates. We have to get the least square estimates for mu, alpha I and beta j by the usual procedure, that is by minimizing the error sum of squares, which is called the least square method or method of least squares. Okay. So, the least square estimates for the parameters are obtained by minimizing the term E is equal to double summation epsilon I j squared, which is nothing but double summation of y I j minus mu minus alpha I minus beta j the whole squared, which is obtained from the model, mathematical model defined earlier. And as in the case of one way classification, so here also the total variation in the data is partitioned into different sum of squares. So, total sum of squares here due to 3 components. The first one, sum of squares due to treatments, and sum of squares due to varieties, and the last one is sum of squares due to error. In notations, we have st squared is equal to s small t squared plus s small v squared plus se squared, and we have the degrees of freedom for different sum of squares. The total sum of squares being computed from n, that is actually hk, because we have k varieties and h curves. So, hk is nothing but the total number of observations n, will have n minus 1 degrees of freedom, and for treatments it is k minus 1, and sum of squares due to varieties we have h minus 1, and finally sum of squares due to error will have h minus 1 and k minus 1 degrees of freedom. And this implies that the degrees of freedom are also additive in nature, that is left hand side we have hk minus 1, that is equal to degrees of freedom due to treatments plus degrees of freedom due to varieties plus degrees of freedom due to error. The next step is to obtain mean sum of squares by the usual procedure, dividing the total sum of squares by its respective degrees of freedom. So, here we obtain mean sum of squares due to treatments, varieties and error, and the test statistic to test the null hypothesis we defined earlier. Since we have 2 factors affecting the values in the data, we have the 2 set of null hypothesis, and here we have 2 test statistic. The first one is for treatments and the second one is for varieties. So, the statistic to test the homogeneity of the treatments is st squared by se squared, which follows f distribution with k minus 1 and k minus 1 into h minus 1 degrees of freedom. And for varieties, the test statistic is defined as sv squared by se squared, that is small sv squared by small se squared. These are nothing but mean sum of squares due to varieties, ratio of mean sum of squares due to varieties to ratio of mean sum of squares due to error. It follows f distribution with h minus 1 and k minus 1 into h minus 1 degrees of freedom. And by comparing the calculated values of f with the table values, respective table values with respective degrees of freedom at certain level of significance, we accept the hypothesis or reject the hypothesis. If the calculated value is less than the table value, we may accept, otherwise the h naught is rejected. And the entire analysis may be put in the form of table called ANOVA table, and for 2-way classification we have the ANOVA table as follows. So, we have 5 columns: sources of variation, sum of squares, degrees of freedom, mean sum of squares and variance ratio. So, under sources of variation we have 2 factors: treatments and varieties, also the error component, and altogether we have total. And sum of squares due to treatments is denoted by st squared, and here sv squared, se squared, and the total sum of square is capital S t squared. Degrees of freedom we have k minus 1, h minus 1, h minus 1 into k minus 1 for error, and n minus 1 or hk minus 1. Mean sum of squares st squared sv square small se square, and variance ratio here for treatments it is ft is equal to small st squared by small sv square. It follows f distribution with k minus 1 comma h minus 1 into k minus 1 degrees of freedom. And the second statistic is for varieties Fe is equal to Sv squared by Se squared. So, here it is Se squared, and it follows F with h minus 1 comma h minus 1 into k minus 1 degrees of freedom. And the summary of our discussion: definition, we have seen the definition of analysis of variance and assumptions underlying the ANOVA test, one-way classification with illustration, mathematical model, null and alternative hypothesis, and F statistic to test null against the alternative hypothesis. And for two-way classification also we carried out the same procedure, that is, we have discussed the two-way classification with an illustration with a specified mathematical model, null and alternative hypothesis, and F statistic. And the questions here we have: explain the meaning of analysis of variance, state the assumptions in the analysis of variance, what is the difference between the variability within classes and the variability between classes, explain how will you split the total variation in two-way classification into variation due to independent factors of variation, describe the various steps in ANOVA for one-way classification, what is two-way classification in ANOVA, and finally give the mathematical model for a two-way classified data and obtain the test statistic to be used. Also give the analysis of variance table, that is ANOVA table. Thank you for watching the UGC lecture series on mathematical sciences.